So now that we have finished what we're going to do with chapter 9, we're going to spend a couple days, pretty much what time we have remaining, giving you a little bit of an introduction to limits. And limits are something that is extremely important when you start taking calculus. So we're going to give you a little bit of a preview of where calculus starts without doing any actual calculus. And we're going to keep these lessons pretty short and the assignment's pretty short just to kind of get through the next week and let things finish up. So for today, we're going to introduce the idea of a limit and limit notation. And I think I've written something very similar to this on the board a couple times during the year as a hint of what is to come in calculus. This notation is called limit notation, and this is read as the limit of f of x as x approaches c equals n. F of x could be any function, x being the variable x, and it's going to either approach a number, or sometimes we look at it as x approaches infinity or as x approaches negative infinity, equals n, where again the n can be a number or negative infinity, positive infinity. F must be a function that is defined on some open interval containing c, but f does not need to be defined at c. And as we go through these examples, you'll see what that means. It has to be defined around c, but not necessarily at c itself. Here are a couple ways to describe the meaning of a limit, and these probably sound pretty similar. One way is to say, for all x approximately equal to c, with x not equal to c, the corresponding value f of x is approximately n. Now remember, when we talk about f of x, what we're talking about there is the y coordinate. So when we're saying when the x coordinates are really close to c, the y coordinates are really close to n. Or another way to say that is, as x gets closer to c, but remains unequal to c, the corresponding values of f of x get closer to n. So again, this f of x is the y coordinates. So we're talking about what's happening around a specific x. For today, we're going to look at these limits and explore them by looking at the table function in the graphing calculator. If you don't have a graphing calculator, you can do each of these calculations separately, but it's quicker to use the table on the calculator. So here, I want to find the limit as x approaches 3 of the function 5x squared. We're trying to figure out what number does 5x squared approach as x approaches 3. We're going to complete this table of values using the calculator. And I need to show you what this is going to do on the calculator. So we want to do is look at what happens as x approaches 3. So in the table, I want to pick numbers that are really close to 3. And if you notice what numbers I have here, 2.9, 2.99, 2.999, these are all numbers that are getting closer to 3 from just below it. And then 3.1, 3.01, 3.001 are getting closer to 3 from just above it. So we're going to look at the table to see what values f of x is approaching as x gets closer to 3. To do this, we're going to go to table set, which is second window, and we're going to change this so the independent says ask. When the independent is set to ask, if you go to the table, you can type in the x's. So we're going to go to y equals, and we're going to type in our function. Evidently, this was the last thing we were doing when we were in school. We're going to type in the function f of x equals 5x squared. So I have 5x squared. And I'm going to go to my table, where now I'm going to type in the x coordinates. And the numbers I'm going to type in are these numbers that we have here. So I'm going to put in 2.9, 2.99, 2.999. So I'm 1/10, 1/100th, and 1/1000th away from 3. And then we go same 1/1000th away above it, 1/100th away above it, and 1/10th above it. And if we look at these values, what we're looking for is what is the limit as x approaches 3. So as we get closer and closer to 3, which would be between 2.999 and 3.001, what are these y values getting closer to? And if we look from the top down and from the bottom up, we see that right in the middle here, it gets closer and closer to 45. So you would, when you do your homework tonight, you're going to figure out some values that are really close, put the number you're approaching in the middle, and then you're going to copy this table that you make on your calculator down. But then to answer the question, what is the limit of, as x approaches 3, of 5x squared? The limit is 45. Now the second question here is, what is the value of 5x squared when x is 3? So if I go back to the table and I put 3 in there, when x is 3, the value is also 45. So I could say that f of 3 is equal to 45. In this case, the limit is the number that the graph actually hits. And that has to do with the fact that 5x squared is a continuous function. And we'll talk more about those properties over the next couple of days. Here's an example where it's not a continuous function. So we want the limit as x approaches 2 of x squared minus 4 over x minus 2. 2 does not work in this function. If I plug in 2, I get division by 0. So we want to look at numbers as x approaches 2. I have 1.9, 1.99, 1.999, and so on. Now, one comment about if you do this on the calculator, if you put it in as a fraction, you will get answers as a fraction. If you want to see answers as a decimal, you need to put the fraction in kind of the old school way of parentheses around the numerator and parentheses around the denominator. Otherwise, your table will be full of fractions that are harder to compare. So I put my function into y1. My table set is still ask. I go to the table, and I'm going to change all of these. So now I want to be around the number 2. So 1.9, 1.99, 1.999, and then a little bit above, 2.001, 2.01, 2.1. I get rid of this one. And if we look here, we see that right in the middle, as x gets closer and closer to 2, the y values get closer and closer to 4. Now, if I plug 2 in this case, I get an error because the function is undefined at 2. So what is the limit? What is my answer? The answer is that it approaches 4. What is the value at x equals 2? It's undefined. But here's something that we can see. This function simplifies. If I take this numerator and factor it and cancel out the x minus 2's, remember that's a hole in the graph, I get that this function simplifies to just x plus 2. And if I plug in x equals 2, I get the same value that was the limit. So on this graph, we look at the graph, this function looks exactly like the line x equals 2, or x plus 2, except that if we trace and type in 2, we get that the value is undefined. So there's a single hole where x equals 2. And so the graph approaches 4 from both sides around 2, but it doesn't actually hit 4. One last example, a function that you wouldn't know the shape of right away. I want to find the limit as x approaches 0 of sine of x over x. And we're going to go around 0, so we need to go into the negative and positive around 0. So my function is y equals sine of x divided by x. And I'm going to go to the table, and I'm going to put in negative 0.1. Sorry, that's me using my computer. Negative 0.1, negative 0.01, negative 0.001, and then 0.001, 0.01, and 0.1, and 1. Oh, hold on. One comment here. Since I'm doing trig, the mode matters. In this case, I really want to be in radians. Otherwise, I'm looking at 0.01 degrees, which is such a small number. So I'm going to go back to my table. And what I see here, these numbers look like they're all the same. If I go over and scroll down, it'll give me more decimal places at the bottom, and you can copy more of these. These numbers are not exactly 1. They are, however, really, really close to 1. And we can see that between negative 0.001 and positive 0.001, the y-coordinates get extremely close to 1. So the limit in this case, the limit of sine of x over x as x approaches 0 is 1. What is the value of this when x equals 0? Well, there's an x in the denominator. If I plug in 0, it is undefined. Just so you can see what this graph looks like. This is a graph. It's a sine function that damps on both sides. It gets smaller on both sides. And if we trace, you see it's not defined at 0, but as you go around it, it goes from 1 down. So it's just there's a hole up at 1. So you're going to do a couple of these tonight for homework. For each one, I'm going to ask you to make a chart of your own with values. You can use your graphing calculators and do it the way that I did it with, again, second window for table set, change the independent to ask. Or you could plug in all the individual values one by one on your calculator or whatever calculator you're using. So a couple more days and we will give you a little bit of a preview of calculus to get you out the door and ready for next year.